So we mentioned before that once the core becomes iron, that's it. There's no more fusion for these high mass stars, these ones that are above even 8 solar masses. Now the reason why fusion ends at 8 solar mass is actually a little bit weird. It has to do with the way that the nucleus behaves. So what we have found is that depending on the number of nucleons, so the number of protons and neutrons that are in the nucleus, the proton and neutron actually have differing masses. I realize that sounds really weird because it seems like it should have the same mass no matter where you go. If you remember previously, we talked about conservation of mass, which means that you cannot create or destroy mass. So how is it that if we put another proton in there, suddenly protons have different masses? Well, remember, the conservation of mass is actually a little bit of a lie. It's not a huge lie. In everyday life, conservation of mass works. But altogether, we actually have to have conservation of mass and energy. Remember, E equals mc squared. So if we have a large change in energy, that's going to be reflected as a large change in mass. Now, when we're dealing with protons and neutrons, they have such little mass, and the nuclear forces that are holding the nucleus together are so very strong, meaning they have lots and lots of energy. This will actually affect the mass that we detect for the protons and neutrons in differing atoms. So what we find is that hydrogen, a proton in hydrogen, has the very highest mass. That's because it has the greatest energy. As we begin to fuse other elements to this hydrogen, we see that the protons decrease in mass. So helium is way down here. A proton in helium has way less mass than a proton in hydrogen. That's just showing us that we have a big change in energy. Well, we get this overall trend of decreasing mass and therefore decreasing energy in the nucleus until iron. In iron, the protons have the very least mass, meaning that they have the least amount of energy. Then, if we continue off to the right, going to heavier and heavier elements, for example, over here we've got lead and uranium, we start to see an increase of mass and an increase of energy again. What this means is you can fuse hydrogen into helium and that will release energy. You can fuse helium to carbon and that releases energy. You can fuse carbon into other things like magnesium or silicon or neon, and that's going to release energy. But if you try to fuse iron together, it will not release energy. Instead, it requires excess energy. It's an energy sink. So once the core has reached iron, it's not going to be able to fuse and generate power for the star anymore. So once we get to iron, fusion in the core now ends. Now, once the core is mostly made up of iron, and it has become large enough that there's enough gravity to it, first it's going to shrink until it reaches electron degeneracy pressure, but as it continues to build up mass, then at some point gravity actually overcomes electron degeneracy pressure. What that means is that the core is suddenly going to collapse. As it collapses, it will reach up to 5 billion Kelvin in 1/10 of a second. Okay? At this temperature, it is so hot that the peak wavelength, the peak type of light that the core is going to be giving off are gamma rays. Now remember, gamma rays are the highest energy type of light. These gamma rays are so energetic that they will destroy the nucleus of atoms. These gamma rays, this light, has so much energy it tears the nucleus apart. In another 1/10 of a second, gravity becomes so intense that the electrons are squeezed so tightly together that they have to find somewhere else to go. Remember, one of our rules from quantum mechanics is no electrons can share the exact same place. Well, what this does is it forces the electrons to combine with protons. When that happens, we have a negative charge and a positive charge, which will create neutral charge. So an electron and a proton will fuse together, forming into a neutron. This also will release a neutrino, if you remember neutrinos when we talked about the sun. Now, as this happens, it is possible for the core to stop contracting when it gets to about 20 kilometers wide. Okay, at that point, it has reached nuclear density, and it will stop contracting due to neutron degeneracy pressure, meaning that it's now the neutrons that are trying to get squeezed too closely together that we now have laws saying that can't happen. Okay, so notice what happened. This thing started out as about the size of the Earth, and in about a quarter of a second, it shrank down to about the size of a city. This is going to release lots and lots of energy. Okay, well, after that happens, we have the outer layers that are then going to start falling in towards that now shrunken core. As this stuff falls, it's going to have very intense gravity pulling on it, which means it will accelerate until it's going at about 15% of the speed of light. Now, as it falls and picks up speed, eventually it's going to hit the core that is now made of the neutrons, and it's going to ricochet. The core is now perfectly rigid, so all of this stuff bounces off. So we now have stuff falling in at 15% of the speed of light, and we'll have stuff flying out at 15% of the speed of light. Now, a quick note. If the core gets too large, if that thing that collapsed into this ball of neutrons is too big, then it's possible for it to continue to collapse into a black hole. We'll talk more about that later. Now we have stuff falling in at 15%, we've got stuff flying out at 15% of the speed of light. This is going to create a shock wave that is then going to travel through the rest of the star. This is going to create a huge amount of turbulence, mixing up all of those distinct layers, and then finally, somewhere around 5 hours after core collapse, the shock wave finally hits the surface of the star, and we see the star explode as a supernova. And so this is what triggers most supernovae. In this image, sequence of images, we're actually looking at where different elements are located. So this is images of a supernova remnant, Cassiopeia A. In the left piece, we're looking at where the silicon is located. In the middle, we've got where the calcium is, and then on the right, we're looking at the iron. Now, what I want to point out is notice there's no distinct layering. Everything is well and thoroughly mixed as that turbulent shock wave is passing through the star. Now, when the star actually explodes, up to 96% of the star's material is ejected back into space. What this is going to do is increase the amount of metals in the interstellar medium. Now, during the supernova, we have so much excess energy. Remember, we've got stuff flying around at around 15% of the speed of light. We have so much excess energy, we're able to fuse beyond iron. So in the normal processes of a star, the core does not get beyond iron because iron does not release energy. However, during this supernova, we have so much energy that we're able to fuse beyond iron. Now, it's not going to release energy, it's an energy sink, taking away that energy, but we're able to produce every element beyond iron that we see on the periodic table. Now, a supernova will have a peak luminosity of around 10 to the 9th solar luminosity. 10 to the 9th is 1 billion. A supernova will put out as much energy as 1 billion stars. We've actually detected some supernova that put out as much light as the entire galaxy in which we see them. If you added up all the light from the galaxy, that would be equivalent to the single supernova that we see. Now, based off of the spectra we see for supernova, we actually define 4 different types. There's type 1, which has little or no hydrogen. We don't see any hydrogen in its spectrum. We then subdivide type 1 into 3 different subtypes. Type 1A, 1B, and 1C. Then there is type 2. Type 2 shows hydrogen emission. Okay, so our 4 different types are type 1A, 1B, 1C, and type 2. Now, each of these is produced by a slightly different progenitor, meaning that we actually kind of know what was going on with the star before it exploded. A type 2, which is the ones that show hydrogen emission, these come from core collapse of a regular boring normal supergiant, a star that still has all of its layers and still has a large hydrogen envelope. when the star explodes, that causes the hydrogen to become heated enough that it then begins emitting light, giving us the hydrogen emission. Type 1c is also caused by the core collapse of a supergiant. But in this case, something has happened to the star so that it's lost its hydrogen and its helium layers. Maybe it was part of a binary companion, we'll talk about that later, or maybe it had flares that allowed these other layers to be ejected into space. So it doesn't have hydrogen or helium layers. Type 1b is similar. It is still a supergiant going through core collapse, but in this case it still has the helium, but it has lost its hydrogen layer in some way. The last of the supernova types is type 1a, and it is not produced through core collapse of a supergiant. Type 1a is caused by a completely different mechanism, and we actually don't have the information yet to explain it. We will later on, so you'll just have to wait a bit.